My name's Callie Babbitt, and I've come in from Rochester, New York to talk to you all today about life cycle assessment and life cycle thinking as it relates back to sustainable energy systems, which I think is what most everyone here is kind of dealing with in one way or the other. Before we get started today, we wanted to build in a little bit of time at the beginning for a little bit more of an informal discussion. Who are you? You know, if everyone can introduce themselves, what area do you work in, and what are your interests in either energy or life cycle assessment? What are you hoping to get out of this, and how it might feed back into your own research or studies or professional activities? So, because I want to be able to, you know, as we go through, add details or examples that kind of fit back into the areas that you all are working in. So it'd be great if we could go around and learn a little bit more about what everybody's doing. And then the one other thing I'll mention is that I think you'll probably be tired of hearing this by the end of the morning, but we're supposed to remind you lots of times. There is a survey that at the end of the lecture you are supposed to take, and there are a couple basic, it's a very short survey, your affiliation, your position, your previous background on life cycle assessment, or LCA, the abbreviations here, and then a few questions about whether or not this seminar actually improved your understanding or appreciation of the method. So it's a pretty basic thing, but we'll be chasing you all down and tackling you if we don't see a blue sheet in our hands at the end of the session. But with that said, I thought maybe we could just go around and I'd like to, you know, kind of get to know you all a little bit better before we jump in. So I'm not sure if there's a guinea pig. You want to start over here?
Hi, I'm Katie Peterson. I'm a student at Case Western, and I'm an intern at Great Lakes Energy Institute. I'm interested in energy research. I'm a biomedical engineer, but I haven't had much experience learning about this type of research. So since starting at Great Lakes, I've learned a lot about the different initiatives they have going.
And I think the microphone, it's not for in here. I think it's to pick up for the recording they're doing.
I'm Kyle Peters. I work in the physics department. I'm a PhD student. I work a lot with self-assembling biomaterials, and I'm not really sure what this whole presentation entails, but I imagine it will help out with the research in future years.
Hello, my name is Freddie Arce, and I'm currently an undergraduate here at Case, and I'm studying biomedical engineering and polymer engineering. And over the summer, I'm doing research on antibiotic wound dressing materials. So I guess the life cycle analysis will help with like biodegradability and stuff.
Good morning, I am Saman. I'm a graduate student at Civil Engineering Department, and the topic was interesting for me, especially the life cycle assessment, general for buildings, not energy systems, and I'm not sure that that's proper seminar, but I hope that I can get this from that. Thank you.
Hi, I'm Catherine Starr. I'm an undergraduate materials science major at Case. I'm currently doing research in the chemical engineering department, but I want to eventually work in the solar industry, and I know we have a lot of like life cycle solar degradation research here, and I think that this might be a good addition to that if I get any experience in that field.
Hello, my name is Ryuji Fujita. I'm currently an undergrad at the University of Illinois, and I want to go into the civil engineering program, and I'm actually an intern of Professor Polino, and we're interested in LCA, so I hope to gain a more broader and deep understanding of that today.
Good morning, I'm Suneva Collins. I'm an associate professor in the Department of Mechanical and Aerospace Engineering. I teach the design and manufacturing cycle to undergraduate students at the sophomore level and at the senior level. And part of that course is this idea of life cycle assessment in terms of materials choices and design choices. So I'm here to pick up anything I can on that area. Thank you.
Hi, I'm Ethan Pickering. I'm a undergraduate BSMS student from the Mechanical and Aerospace Engineering Department. Right now I'm doing some building energy efficiency data analytics, basically looking at some electricity usage and using data analytics to give back recommendations for efficiencies. and also working with the Green Lab audit team this summer to look at labs and assess their ability for sustainability. So that's why I'm here today.
I'm Trisha. I'm an undergrad here, and I'm working in the materials science department, working with improving longevity of photovoltaic cells.
Hi, I'm Mike Polino. I'm a faculty member in civil engineering, particularly in the area of structural engineering. And I'm interested in LCA for assessing structural designs from a sustainability perspective. And I'm also interested in LCA in research and assessing the performance of structural systems under high hazard loading, and using LCA as a tool for evaluating different designs.
Hello, my name is Matt. I'm a chemical engineering student here at Case. I'm just here to learn anything new.
Cool.
No specific reason.
Hi, I'm Tori Eldridge. I just graduated with civil engineering. I've learned about life cycle assessment a little bit, but I'm more just looking to broaden my knowledge and how it can apply to structural design.
Hello, I'm James Whiteman. I'm in engineering management and industrial automation. And I've done a little bit of life cycle work when I was working at Rockwell Automation, and that was a few years ago, and I wanted to see what was going on right now.
Cool.
I'm Tiffany McNamara. I work at the Great Lakes Energy Institute, and as a part of the NSF PIRE Award, we are doing some life cycle assessment 2 years ago and this year. And we will then eventually add this to our award website so that we can also host a little bit more information about the process on there. So I'm just here to host it and learn.
All right. Okay, so should we go ahead and get started?
Sure.
All right, let's get started, and then if folks come in, we'll grill them on what they're doing here as well. All right. So just to give a little bit of context about, I guess, the scope of what we're going to try to do today. Life cycle assessment on the surface seems like a pretty easy method. Oh, think about the entire life cycle of a product or process, collect some data, analyze the environmental impacts. It turns out that there's a lot of challenges in actually implementation. So what I'm not trying to do is cram an entire how to do an LCA into one day. That's kind of impossible. But what I do want to accomplish today is to get you to appreciate how it can be used. And now I'm really focusing on sustainable energy systems, since that's the topical area of the grant, how it can be used to inform the design, the development, the assessment of these energy systems, and why it should be used. What sort of new insight it gives that you wouldn't get from like traditional engineering or science research. But I also want to sort of say, how is LCA being used? So we're going to walk through a case study, we'll talk about the methodologies, and then this afternoon there's a smaller workshop on, I have some Excel tools, and we're going to actually get into crunching some numbers and actually doing some very simplified like mock LCAs. I think there's probably a little bit of room left for this afternoon if folks want to jump in. More than happy to have you all join us for that. I'll say a little bit of introduction about myself as well. So I'm here from Rochester Institute of Technology and specifically the Golisano Institute for Sustainability. Now this is a kind of unique institution. It is a degree granting program. We offer degrees, PhD in sustainability and a master's in sustainable systems, as well as a professional architecture master's with a focus on sustainability. It's kind of the equivalent of a college. Our tenure lines and our degrees are in sustainability, not in engineering or something else. And what that allows is us to do work that's very interdisciplinary. So you can see our facility here. It's a LEED Platinum facility, and it's also a living laboratory. I'd love to talk to some of you building researchers, because one of the things that we're grappling with in this system is that there's 1,500 sensors all throughout the building that are collecting data every 5 minutes on lighting, occupancy, air quality, all electricity use. And so now we have a big data challenge in terms of figuring out what to do with this information. But it's a great living learning lab, and you can see there's my lab here and some other facilities. We do a lot of work with industry as well as with traditional funding agencies. We have a number of international collaborations. We're a member of the Clinton Global Initiative and the Ellen MacArthur Foundation for Circular Economy. And we try to do some outreach and community engagement in terms of helping Rochester become more sustainable. And so I wanted to give a little bit of introduction of myself as a means of kind of diving into the topic. So I came to this program because at the time, they were only one of 2 in the country that offered a PhD in sustainability, the other being Arizona State University, where I worked before coming to RIT. But Arizona State's focus is more on urban systems. And my interest is really more on the industrial side. And that came about from a very early age. I'm from a small town in North Florida. And this is my family's property. We own a plant nursery. And so growing up, our livelihood was really invested in the health of the natural ecosystem. We basically relied on nature for our economic health. But at the same time, we also have this industry in my hometown. Any guesses? Anybody? What sort of industry we're looking at there? A big pile out there is a big clue. So this is a pulp and paper mill. The town I'm from is affectionately known as the pine tree capital of the South. But this is a very long-standing pulp and paper mill. They make a lot of the fluffs pulp for diapers and other things. And it's also a major draw on local resources and a major pollutant. So, I don't know if you've ever driven by a pulp and paper mill. It smells like really lovely, right? It's like rotten egg smell. In my hometown, though, they say, smells like bacon and eggs, because this is the economic lifeblood of the community. The community would collapse without this industry here. And so there's this I grew up with this very interesting balance between relying on the natural environment and also a lot of recreation, hunting, fishing, and things like that. And then this idea that you had to pollute and exploit the natural environment to profit. But growing up, I saw that all the engineers who worked at this mill were the ones in the nice houses and the nice cars. I said, I want to be a chemical engineer, which is my first degree. And here I am. This is photos in 1997. I'm a very, hard at work co-op student. I did my co-ops back at this pulp and paper mill. And many of the tasks that I was assigned to work on had to do with tackling process changes or complying with regulations to meet some sort of new environmental policy. And I was very naive at the time, so I asked my boss, why don't we try to tackle the long-term problems? Why don't we look 5 or 10 years out into the future and anticipate what the next environmental regulation is going to be and then come up with more effective solutions? And he was very nice. He didn't say, like, is the economy stupid? But basically, that was the take-home message. We have a bottom line to meet this quarter. We can't invest tons of money into all this future design and sustainability. And so that was the first time that the light bulb really went on for me, is why can't we design technologies that are both environmentally friendly and more cost effective? So that's sort of what set me on the path of going in this direction. But as I went and as I've begun doing this research, I realized that even if I'm working as an engineer and working at this mill or wherever, even if you're not a sustainability practitioner, every decision you make is a sustainability decision. And I have a colleague in industrial design who often says, we're not designing products, we're designing consequences. Okay? And so this is what really sort of started inspiring me to study more about sustainability, and what eventually led me to RIT, is this idea that working in that mill or whatever engineering job I might work in, I'm ultimately designing things that will have some sort of impact on nature, on our environmental and our economic health. Now, we don't always know what these consequences are. Sometimes they're removed in space. So when we came into this room this morning and turned on the light switch, we got the light here, but the environmental impact of producing that light came farther from this point. I don't know, where do you get most of your power here in Cleveland? A lot of coal burning, okay? So the first place that most of this impact is felt is probably wherever these coal power plants are, okay? So the impact isn't felt here, it's maybe felt 50, 20, 50, 100 miles away, depending on where these are located. Coal makes up 50% on average of our of our electricity grid in the United States. So it varies quite a bit by region, but coal is a significant fraction. And everywhere that we burn coal, we're also introducing new impacts. Some of these are global, like carbon dioxide, and some of these are very local. When you burn coal, coal contains just about every metal element that we know or think about. So you're also releasing arsenic, mercury, chlorine, other gases, things like that. And so there's an impact here. This is often exacerbated by the fact that these are typically sited in lower income areas. Now, not always, but depends on the zoning laws. But these impacts are often disproportionately felt by those who live in these environments. Okay, so my decision to design a product that used energy or to turn on a light here has now created impacts 50 miles away. Well, the coal has to come from somewhere. And so now I've expanded my geographic scope another 100,000 miles, depending on where I get the coal. And in our system, there's usually baseline sources of that coal, Illinois basin. There's also spot sources, so we might even be bringing it in from Wyoming or from South America. And so there's huge impacts here as well. The land depletion, once the coal is mined out and extracted, the overburden and the tailings, the waste that's left over is put back into the mine often. And so then as you have slightly acidic rain and things like that hitting this area, you're getting all of those metals leaching back out into the local ecosystems. Okay, so my one decision here has now had consequences that have spread over maybe 500 to 1,000 miles. These consequences are also removed in time. And I think this is one of the most challenging things to kind of accept as an engineer, because we really think about our human innovations as being the peak of society. But it's often very difficult to think about how these innovations are going to have ripple effects into the future. So I often pick on this gentleman, Thomas Midgley. He was the GM engineer who in the 1920s discovered that lead worked really well as an anti-knock agent, for gasolines, misfiring of the pistons. And he also was the one who discovered that chlorofluorocarbons made for really good refrigerants. So what's the problem with the CFCs? Ozone depletion. And so sometimes he's actually referred to as the individual who single-handedly did the most to damage the environment, right? But what a phenomenal engineer, right? He had a technical problem, refrigeration, engine knock, and he came up with an appropriate technical solution. There's not any consideration of how this might then impact future generations. And this cycle has continued on. So our decision to lock into personal automobiles as our form of transportation has continued to have impacts over time. So we found out later on that lead, of course, is a neurotoxin. We probably shouldn't be putting it in our gasoline because it gets into the air and it gets into the groundwater. And so methyl tert-butyl ether was now introduced as both this octane enhancing additive. And then when the Clean Air Act amendments came about in the 90s, they also said, oh, it also works really well as an oxygenate. It helps the fuel burn cleaner, more complete combustion. And so we replaced lead with MTBE. Fast forward another 20 years, they're starting to suspect carcinogens in this compound. And so what do you see when you go to the gas station now? May contain 10% ethanol, right? So now we've switched to another compound. So states really took the action here versus federal, switching out from MTBE to ethanol as an additive. Now, right now, this ethanol is from fossil. It's a byproduct of oil distilling. It's not like corn-based ethanol, although conceivably it could in the future come from bio-based sources. And the question is, well, is this a perfect solution? Given the trajectory we've been on, probably not. We're just not quite sure what all of the impacts are going to be. It could very well be that it changes, it helps solubilize some of the compounds that are in the gasoline, like the BTEX, benzene, toluene, ethylbenzene, xylene, so that when the underground gas storage tank eventually leaks, which it will, that it will change the patterns of those plumes in underground aquifers. We don't know yet quite what will happen. But the point is that we every time we run into a problem, we put a Band-Aid on it. and this introduces new problems. Life cycle thinking is not perfect. It's unlikely that in 1921 someone said, oh, you should do an LCA on that. You want to evaluate the trade-offs of lead. But now that we do have these tools at our disposal, it's irresponsible of us as scientists and engineers to imagine that our technologies are going to be introduced into a void. They will have impacts, and we may not even be around to bear them, but our children and grandchildren might be. Now, the other thing that we often think about is I'm going to design this technology and it's going to solve a certain problem. I'm going to design a more efficient solar cell and produce renewable energy. I'm going to introduce electric vehicles and reduce emissions. But every time we make a change in one system, it again has consequences that ripple out into many other systems. So the electric vehicle, for example, you have to have electricity. So now this has impacts on our grid, changes the way we deploy electricity, changes the need for different types of fuel sources at different times of the day. Maybe we're going to produce this electricity from solar power. So now this puts an additional demand on photovoltaics and the materials that are used in these products. We need a battery to store the energy. So we need to design now energy storage systems. And the most common chemistry is, of course, the lithium-ion battery, which is what a lot of my research deals with. And this has implications for lithium demand. Do we have enough lithium? Probably yes, but there's other minerals that we might be a little bit more concerned about. And you can see here, this is a graph of lithium, world production of lithium from way back in the 20s to 2005. It's only gone up since then, and you can see in the last 10 years it's really skyrocketing because of, not yet because of electric vehicles, but from portable electronics. We only expect that to continue with the vehicles. And now once you've put these vehicles these batteries in the vehicle, you also have to get them out at end of life and smelt them or somehow recycle them to recover the materials contained. So our decision about vehicle electrification, which might be a goal from, the president has a goal about vehicle electrification, we're all doing research on this, we have to realize that there will be so many other systems that this touches. And then the other area to think about is that there's a lot of different stakeholders at play here. Those of you all who have worked in industry or do any sort of collaboration know that none of these things can be developed in isolation. So we're thinking about now this entire life cycle from raw material all the way to disposal, cradle to grave. And along the way, you're going to have a huge array of stakeholders. The industry, the corporations, they might be thinking about their supply chain. They might be thinking about their own operation. The recyclers, so in some products there's regulations requiring a manufacturer to take the product back at the end of life. So that's a new stakeholder. You've got your consumers. It's often very difficult to even think about how consumers might use the products and technologies that you're anticipating, especially you building folks. Legislators, municipalities. And then there's one stakeholder on here that's not, or there's one that's not on here that's also important. Any thoughts on who might not be included here? Say what?
Future humans.
So other future humans, and then humans around the world that may not ever use this product or this service, but that are still, because of this different spatial impacts, still going to bear the consequences of your design decisions. So we can be designing cutting-edge solar technology here, and there may be people around the world who will never benefit from that solar technology directly, but that may have some benefit because we've been able to reduce climate change, or vice versa if it turns out to be a problem. So there's many, many stakeholders. And of course, what this means in practical terms is this is a lot of people you have to get on board with technology adoption and deployment. Okay, so we've got this big problem. It's a big, hairy, complex problem because we need, and the only way to deal with this is to really change our perspective from being disciplinary to being systems approach. And this is really the reason that one of the hallmarks of the education program at RIT is this idea of a systems thinking. None of the decisions we're making happen in isolation, they happen in a system. And so we have to be able to integrate all of these different dimensions. So what this sort of might look like, many of you are really probably some of you I'm guessing are working here. You're in the lab, you're testing materials, or even if you're not in the lab, maybe you're doing modeling, really fundamental research on different topics. But all of that ripples back out. At some point, that technology might be deployed. How will it be adopted? How will it be used? Will it be used in the way that it's designed or in some different way? And then at some point, this deployment has impacts on the broader environment, and ultimately there are some impacts on society as a whole, social needs and wants. So this is not something you normally learn in an engineering class, right? So this is why life cycle assessment becomes very important, because it is a methodology that gives us an ability to at least start to capture the big picture, to start to capture this system's perspective. All right, so what is life cycle assessment? A lot of definitions, a lot of people doing this now. As any time that a methodology or something becomes more popular, becomes a lot of buzz. Like earlier this year, Walmart put out an announcement saying they're now going to have a green store where online you can buy products that have been assessed with life cycle assessment and make your decision based on green designs, green attributes. So there's a lot of popularity around the method and a lot of people doing it in different ways. But the basic idea is that it's at least supposed to be an objective process by which we can actually evaluate these systems level impacts, starting all the way back at material extraction, processing, manufacturing, use, waste management, and then the return into this. And I'll just mention, the reason this becomes very important is because doing this gives us new insight on our technologies that we might not have otherwise. For example, I do a lot of work with electronics, computers, electronic waste, and there's been a lot of effort in the last several years to reduce the energy consumption, especially in standby, because products spend a lot of time in standby. So we've done a really good job of making computers more efficient. But is that the biggest impact of a computer? Any guesses as to what the biggest environmental impact across the whole life cycle is for a computer, like my laptop computer here?
Disposal.
Disposal, so waste management. Any other guesses? One of the biggest impacts is actually the semiconductor, the little tiny microprocessor. And one of my colleagues has published a paper called the 1.7 kilogram microchip. So to make that tiny semiconductor, that tiny integrated circuit, takes 1.7 kilograms of materials. A lot of that's fossil fuels because it's extremely energy intensive to refine silicon and to produce this high purity device. So when you take a life cycle approach, you get these very surprising results often that say, maybe we shouldn't be investing all of our money into energy efficiency of products. Maybe we should be thinking about green design, alternate processor technology, or a lot of the reason that impact is so large is because consumers only use the electronic for a short amount of time, so designing the product to be used longer. So life cycle perspective can really change our understanding about the systems that we're working in. All right, I want to now talk a little bit about how it relates specifically to sustainable energy systems. But before I move on, are there any questions so far, comments, thoughts? Feel free to jump in at any point and just let me know if you have questions.
Is the Walmart thing marketing, or is it very legit? I'm just curious.
Well, I'm sure that yes, it is at its heart marketing, but it does have some basis in actual life cycle research. So they've partnered with a group called the Sustainability Consortium, and they've made a number of requirements that many of their supply chain now will have to disclose their supply chain information in order to sell at Walmart. Now, it's not universal, it's only for certain product sectors, but there are researchers that are doing the research that backs up the idea that Walmart's going to sell sustainable products. The challenge for me is that they're taking all the complexity of a life cycle assessment and putting it into a single scorecard, and that may not always give the richness of information that an LCA provides, but a lot of us feel like maybe it's a first step, and if people's awareness can be raised, then it's at least doing a little bit to help. Yeah, I'm sure there's not the purest of motives, but I won't. I won't comment. Yeah. All right, so let's talk specifically about energy. All right. So why energy and sustainability? Have any of you all seen gapminder.org? Or does anybody watch, if anybody's watched TED Talks, this gentleman, Hans Rosling, has the most amazing TED Talks. He does all this really cool data visualization. And I really love this site because it really gets at our understanding of the world around us. So Gapminder, you can just Google his name and you'll find a number of really great TED Talks about this topic. But what this site does is it takes a whole bunch of sustainability information and presents it in a really easy format. So in this case, what we're looking at here on the y-axis is the Human Development Index. Now this is a composite metric that looks at things like literacy, democracy, people that live in or out of poverty, gender equity, environmental protection, all of these things in a society that really signify that this society is developed versus developing. And this is plotted against energy use per person. Now both of these are on a log scale. The colors that you see correspond with the regions, and then the size of the circles correspond with the size of the population of the country. So you can pretty easily say, okay, here's the US up here, no, that's China, India, and some things really jump out, and you can see, a lot of the African nations here, et cetera. And so the reason that energy becomes so important from a sustainability perspective is that when we try to do sustainability, that often means that we're trying to accomplish environmental goals, economic goals, and social goals. You may have seen the representation before of a three-legged stool. If any one of those legs of the stool is cut off, the stool will fall over. And so this gets back to the idea, if you make a green technology but it's not cost effective, it'll never be adopted. If you make a product that has environmental benefits, but it's not available to certain parts of the society or that might have negative impacts on parts of the society, it's not truly sustainable. So these kinds of data really help us get at that three-legged picture of sustainability. And it's clear in looking at this that there's a really strong correlation between the energy people are able to use, and this of course is also a surrogate for economic health of a country. So this, you could also look at gross domestic product or other things. That development correlates strongly with your availability to use energy. But at the same time, when we look at the same set of data, and now we're looking at yearly CO2 emissions, and this is per country, not per person. If it was per person, China would be farther down, and the energy use total by that country. And of course, no surprise, I think, to most of us, that these correlate directly. The more energy we use as a country, the more emissions we produce. And you could put almost any environmental metric on this y-axis and see the same relationship. Again, a lot of this has to do with the fact that our energy comes from fossil fuels. So the more energy we use, the more fossil fuels we burn, the more acid, sulfur dioxide we put into the air, producing acid rain. The more fossil fuels we burn, the more mercury we put into the air, creating toxicity. So energy is a really good surrogate for getting at some of these environmental metrics. And there's a clear correlation here between energy and CO2. Well, why? Okay, well, one reason is that we consume a lot of energy. So no matter what technology you're using to produce it, there's going to be a lot of emissions. Okay, so our traditional sort of engineering single discipline focus might say, okay, make more efficient technologies. Okay, and I won't pick too much on the building people here, but what happens, LEED building. Are you familiar with LEED program, Leadership in Energy and Environmental Design? It's like a certification or scorecard for buildings. One of the things that we often see, you design this LEED building, you get a lot of environmental credits for doing this, and then you start operating it, and it doesn't perform quite the way you would anticipate. Maybe the energy savings aren't as great. Why not? Why do you think that there might not be as big of an energy savings as you would expect? Any guesses?
Can't control how the people use the building.
You can't control how the people use the building. When I first moved into my office in that beautiful LEED Platinum building, there was a really complex thermostat on the wall, and all I knew is that I was cold. So I'm like, up, right? And so it wasn't until later they actually gave us instruction sheets that this is how you use your thermostat. You know, do this and then wait, and then, or even the lighting system. So the performance of the technologies depends increasingly, the more high tech we get, the more they depend on the user. And this is what we often call the rebound effect. Has anybody heard that term before? This was very popular a number of years ago, but we see it more and more. You make a product or a technology more energy efficient, which usually means it's also cheaper, and people use it more. You replace your incandescent bulb with a compact fluorescent, and you might leave it on for longer because you know it's saving energy. For many vehicles, although there's some research now showing this isn't true for electric vehicles, there's some research for hybrid vehicles. You buy a hybrid vehicle, and then the owner sometimes will drive farther miles per year. You go into a green building, or you go into a room where there's a motion sensor or something like that, and you might leave the room and not turn it off. I mean, it'll eventually turn off, but there's not quite the same benefit you would expect. And what we normally see is a rebound effect of about 20 to 45%, meaning that if you got 1 kilowatt hour energy savings by using this technology, you'd really only realize about 0.6 to 0.8, 60 to 80% of that energy gain, because 20 to 40% would be lost to this rebound effect, people using the technology wrong. And so whenever we think about making more efficient technologies, we also have to think about how they're deployed. And again, getting back to the electronics example, this is one that we've seen quite a bit. So we did a life cycle study where we've done a life cycle on a single computer. We found out that the semiconductor is a big problem. We said, but over time, it's getting more energy efficient to make and to use computers, but the net impact is going up. Why? People keep consuming more. We don't just own a single computer, we also own a smartphone, a tablet, a printer, etc. We're using them for more amounts of time. And so it turns out that the net impact of this electronics in our household has gone up by 300%. Right? So the individual product energy use has gone down, the net household energy use has gone up significantly because of this rebound effect. Okay, so we have to think about how people are actually going to use the product. And for some of you all dealing with really high-tech devices, do you have to train a worker how to use it? Do you have to, the person who's on the plant floor actually operating it, do they need more information about how to actually use this technology to actually get? For buildings, a lot of times you find that green buildings don't get the savings that you expect until you do some sort of post-occupancy training, teaching the users how to use the building better. Okay, another reason why energy and CO2 are such a big problem is that energy conversion is extremely inefficient. Okay, so how many of you all have seen a diagram like this before? Okay, I love diagrams like this. This is called a Sankey diagram. It's named after an Irish engineer who probably almost 80 years ago came up with the idea of modeling energy flows through a steam engine to show how much was lost and how much was efficiently converted. So second law of thermodynamics. And in these diagrams, the thickness of the line that you see correlates to the magnitude of the flow. And so what we have in this diagram is the US energy use in 2011. And the total amount is 97 quadrillion BTUs, or quads. And on the left-hand side, what you have are the sources of this. So solar, nuclear, somewhat, solar, wind, geothermal, tiny, infinitesimal, probably not even totally proportional to the thickness because it would be hard to see. And then you have the more conventional sources like natural gas, coal, and then petroleum. In this middle, what you have are the applications. What are these energy sources used in? So you can see most of coal goes into electricity generation. Most of the petroleum goes to transportation. But the point that I want to draw your attention most to is on the far right-hand side. What we have here are divided up between energy services and rejected energy. So rejected energy, think about like the entropy, the second law. This is the amount of energy that's lost as waste heat. 41%, or about 40% of the total, is actually of the energy we put in. The energy contained in the bond, the carbon-carbon bonds, the radioactive decay, the solar energy, about 40% of that is actually converted to useful energy. Almost 60% is lost. Now, energy is not lost, but it's lost in terms of its useful value. It's waste heat. And so sometimes I show this image to people in business, and but that doesn't make any sense. Why would you operate a business that was lost so much money? Well, right, you wouldn't. But we operate our energy system in a losing proposition. We lose more than we're able to recover. Now, obviously, there are many thermodynamic limits to the actual conversion efficiencies of our technology. But the reality is that we are limited in a great deal by efficiency. And I know that most of you all working on renewable energies are thinking, how do you push that efficiency up even just a tiny bit more? Okay, so energy conversion is inefficient. So our traditional strategy is make the conversion, make the devices more efficient. Get that solar panel up by 1%. Get the wind turbine up. Make these processes more efficient. Eke out a little bit more efficiency on, from our natural gas and our coal plants if we can. Now, the challenge for this is that in order to get an increase in efficiency, you have to give something. If you're designing a solar panel, maybe it's the addition of some new material. Maybe it's going from a single junction to a multi-junction device. Your efficiency gains are almost never free. Okay? There's some amount of input that has to be put in. And so our life cycle thinking tells us that we need to think about whether or not those efficiency gains are going to be offset by additional requirements in the upstream. Will the additional materials, will the additional processing steps add too much to where it's not worth it, right? And this is where we come up with ideas like embodied energy. And this is the idea, this is the life cycle energy, all the energy that it takes to make and deliver a product or a fuel. We might also think about energy return on investment. This is the ratio between the total amount of energy that it takes, that you get from operating an energy conversion system divided by the energy you put in. And obviously higher is better. So when we first introduced petroleum fossil fuels, we're talking about EROIs of like 40. You've all seen like the Beverly Hillbillies. He like walks out, he shoots the ground, and oil spurts out, like no energy investment, and you got all the crude oil out, right? So that was, over time, I mean, back in the day, that was really the case, but over time, the availability of energy has gone down. So we have to work harder and harder to get it out. So the EROI goes down. But obviously, you'd want it to be over 1. Otherwise, it's not worth it. But you can use LCA to actually determine this. And then the other one is energy payback time. And you see this a lot with solar panels. How long does it take before the energy that this device produces pays off the energy that you invested putting into it? Okay? And all of these are metrics that you will quantify with LCA. Because the only way to know, say, the energy it took to make a device is to actually trace through that whole life cycle. The energy to mine the material, to refine it, to manufacture, to transport it, and then to use it. And once you know all that information, then you can compare it to the amount of energy that it delivers. This is actually a pretty common one for folks that are working in renewable energy systems. This is a pretty easy one to tack on to your research, sort of to add in as a complementary piece of your research. Okay, the other thing that I want to mention, the other problem here, why energy and environmental impacts go hand in hand, is that right now our energy production is extremely carbon intense. Like we've said, our energy comes from fossil fuels, which contain a lot of carbon, which when they're combusted are released as CO2. Another great Sankey diagram. Okay, on your far right, we have the greenhouse gases. These are adjusted, these flows are adjusted for the fact that different greenhouse gases have different impacts on the climate. For example, methane is 25 to 30 times worse than CO2, carbon dioxide, as a greenhouse gas pollutant. It oxidizes in a different way, it absorbs energy in a different wavelength. But these flows are already accounting for their relative magnitude. And still, CO2 is the big one. This is our main greenhouse gas responsible for climate change. Okay, so if you trace back, you can also see the activities that actually generated this, and go back a little bit further and you see which sector these activities are occurring in. And this orange is energy, right? So energy is responsible globally, this is world GHG emissions, for over half of all the CO2 emissions entering the atmosphere, or all the greenhouse gas emissions entering the atmosphere every year, and almost entirely responsible for the CO2 emissions. Some also come from what we call land use change. Cut down a forest, and all the carbon stored in those trees and all the carbon that those trees can take up from photosynthesis is lost. There certainly are other sectors like agriculture. We'll have a colleague who studies life cycle assessment of foods, and it turns out, does anybody know which foods create the most greenhouse gases? Meat, specifically beef. Cows make methane, and they make a lot of manure, which releases greenhouse gases. And so a lot of my colleagues advocate for this idea of like a meatless day, or cutting out dairy and beef for 1 day a week can have more benefit from a CO2 perspective or a greenhouse gas perspective than buying all of your food within a 100-mile radius. Like going completely local, you can get more impact by just cutting out one beef and dairy meal a week. Now, if you're already vegetarian, then that's a different strategy. But if you're a meat and potatoes person, then that's if you can go one day a week without it, you're helping a great deal. Okay, but the point is that this all comes back to energy. A lot of it's transportation, but a lot of it's electricity and heat, both of which are extremely inefficient, both of which fossil fuels. And so we want to say our solution, make low carbon energy sources. And this normally means renewables. Now there's a lot of advocates for nuclear. We won't really talk about nuclear today, but there are a number of people, including Jim Hansen at NASA, who's a very strong advocate for nuclear in our fuel mix. But we're going to talk specifically about renewables. And then we're going to think about the life cycle thinking behind this. Are we creating the next CFC or the next lead additive when we make a new type of photovoltaic or a new type of bio-based material or a new type of wind turbine? Are we actually going to create a net reduction in the carbon that's produced from generating this energy, or are we creating new environmental impacts? So we're going to think a little bit about that now, because when you think about deploying renewable energy, there's a lot of pieces to this puzzle, right? First of all, we just have to put more out there. You saw on that one graph where solar, wind, others are teeny, teeny, tiny line. We've got to put more out there, more technologies. Well, that means it has to become more efficient, higher and higher conversion efficiencies. But we're actually doing pretty good in this area. The cost of solar is going down significantly. But it also means we have to think about energy storage, another systems level impact. The sun and the wind aren't always producing energy around the clock, so we need to be able to store it when we can. And then there's a lot of upfront production costs for most of these technologies. So I'm guessing that for those of you all doing research in the energy area, many of you are working on one of these challenges, right? Is that fair to say? A lot of you energy folks are working on probably one of these challenges or a related challenge, all right? And so any one of these that you might be working on, you're going to have to think about these potential ripple effects. By making this material, by making this solar panel, will I use a scarce material? Anybody here works on something involving transparent electrodes, indium? You know, if you're going to have a solar panel, you're probably going to have some sort of, or how about this? Anybody own a smartphone? Right? The screen, indium. Indium is increasingly a concern for scarcity. Right? But it's also an essential part of many of our energy conversion devices. Okay. We might also be making technologies that are very, very energy intensive or toxic. Anybody working with nanomaterials? Nano architecture? Okay, you get the sustainability like dunce hat or something. No, I'm just kidding. Yeah, all of these have huge promise, but they all have some potential impacts. Maybe they're toxic, maybe they're too energy intensive. And then I would guess that all of us are working on technologies and systems that introduce waste at some point. Well, there's a lot we can learn about new waste streams. All right, so we're going to talk about each of these in more detail. Before I get to that, are there any sort of questions or comments or thoughts? We're going to spend the next little bit kind of diving into these areas. Everybody good? Okay, well, let's jump in. Let's think about some of these cases where life cycle thinking gives us new insight about promising low carbon or carbon-free renewables. One of the most hotly contested areas in this field is biofuels. We at RET don't do a whole lot of work on crop-based biofuels. We work a lot on waste-based biofuels, so taking food waste and producing it, which is another issue. But there's a lot of excitement around the idea of crop-based biofuels, raising cellulosic crops, raising different types of energy crops to actually convert to fuels like ethanol or butanol. And so the reason there's a lot of attention for this is because it's considered by many to be carbon neutral. Okay, as the plant grows, it takes carbon dioxide up from the atmosphere, and that's stored as sugars and starches and proteins and such in there. And this is also a process that's powered by photosynthesis, so low carbon. At some point, this is refined. There might be some food products that come out of this. And then either from the waste or from the crop itself, you're going to produce the energy. Now, this is a case of biodiesel. Anytime you make biodiesel, you're usually, as part of the transesterification process, you usually have some sort of glycerin byproduct. There's a lot of people say, oh, maybe we could convert that to soap, and it's a win-win. And then you're creating a renewable fuel, and when it's burned in the car, CO2 is emitted, but it's the same CO2 that was taken up by the plant as it grown. So one of the original ideas was like, hey, biofuels, great idea, because they're carbon neutral. Do you think that's true? Where are other places you might have carbon emissions? Okay, fertilizer, right? The crops, typically the way we grow crops, there's a lot of fertilizers, pesticides, herbicides. We add a lot of petrochemicals to this system.
Moving putting out the products like the vans and the vehicles and the trains. They hold or use.
Exactly. So all of the logistics, crops don't, if we're thinking about corn, it doesn't grow everywhere. So it grows in a certain area and you're going to transport it. We also have to change out our infrastructure, retrofit vehicles if necessary. But there's another big one. And this is one that got a lot of attention a few years ago. And there's certainly the agricultural inputs and others, but there's also a land use change here. Now there is a lot of upset, social media kind of thing about, oh, we're going to take away crops and we're going to make ethanol, we're going to take the corn away from crops and make it into fuels. That's not quite as big a concern. What is a concern is that anytime you change the economic system, there's huge ripple out effects. And one of the ones that got a lot of attention was the idea that as biofuels become more economic and there's a bigger market for them, it may actually induce other countries to convert their land. Like in Brazil, one of the big concerns is actually some deforestation of rainforests and other areas to instead grow crops. Okay? And so anytime you're changing out this big carbon sink where you have a lot of trees and putting in a crop, you're getting rid of a lot of the soil organic carbon, you're changing the carbon stored there, and you have what's called induced land change or indirect land change. And so depending on how you account for that, there's a lot of studies who are very positive on different types of corn ethanol, sugarcane, cellulosic biofuels. They show a huge reduction over typical gasoline. But then there's also been other studies who say, look, if you take a worst case scenario and you're out there and this causes you to deforest in rainforests and other things, you can actually have an impact that's greater than gasoline. Now, a lot of this gets down to some really nerdy, esoteric life cycle assessment assumptions and details, right? So a lot of it does have to do with the method itself, but it did raise a lot of questions about whether or not this really makes sense from a greenhouse gas perspective. And so now this has actually been integrated a little bit into policy. So there's a number of biofuel standards, renewable fuel standards, ethanol standards that really say, look, you're going to get a little bit of an economic incentive if you're the 20% less than gasoline, which is sort of the standard. But if you can do 20% or more, or you can prove that using LCA, we're going to give you a bigger incentive, a bigger tax credit or a bigger rebate or something like that. So this is a case where LCA findings like this actually fed back into the policy process a little bit, and so now LCA is being used as one of the factors for incentivizing more greenhouse gas friendly biofuels. Okay, I want to talk about nanomaterials. Again, this is an area we do a lot of research on, and two of the big areas that we're working on at RET are fullerenes, so these buckyballs, and we do a lot with C60, so a 60 carbon buckyball, which you can use in things like organic photovoltaics, and I'll talk more about that in a minute. It turns out people also put them in cosmetics, which I don't know why. I mean, I do know why, but it seems crazy. And so we're putting these nanomaterials into new products and creating new impacts. The other one that we work a lot on is single-wall carbon nanotubes used in the anode of a lithium-ion battery. There's a lot of benefits like improved capacity, improved cycle life, reduced internal resistance, things like that. But anytime you're dealing with something at the nanoscale, you have many new issues. It takes a lot of energy to make something at this scale and to make it pure enough to where it'll actually work well in these applications. And then nanomaterials. Will they be toxic? Will they be an issue? Will they poison our environment? We don't know. So here's an example of organic photovoltaics. And this is one of our first PhD students, Anik Anktil. She did a guest lecture for this a couple years ago, and she's at Michigan State now. But she looked at these organic photovoltaics in which you had this 60 carbon fullerene with a functional group added and then used in this organic photovoltaic. And you have this active layer here with both the electron donor and acceptor, which also involves mixing in a very high purity polymer kind of material. And there was a lot of feeling at the beginning. Many of the early studies that were done on this said, look, the material is only going to be in there less than 1%. So if you take the entire device structure, less than 0.5% is even the nanomaterials. Surely that doesn't matter. They're only used in such small quantities, okay? But we actually got into studying this, and so we said, well, let's actually find out. Let's take it all the way back from the carbon source that you might make the nanomaterial to, how you produce it, how you purify it, which actually involves a lot of xylene and solvent extraction, and then a chemical reaction to functionalize it so that you can actually put it in your device. And these are the kinds of results that we got. So this is for the entire organic photovoltaic or polymer photovoltaic cell. And here in this blue is the nanomaterial, the PCBM, which is the functionalized. So the finding was, yes, it's only 0.3% by mass, but it actually becomes 20 to 40% of the total life cycle environmental impacts of producing this. This is the lower estimate. It actually is, depending on which of the fullerenes you pick and how pure it is, it can actually go up to 40%. So imagine that's you know, you have your cell, 40% of the impact is something that contributes just a tiny speck by mass. Okay, so this really changed our understanding of this, and it also changed the way we thought about this, because we can also look and say, well, what are actually the parts of this life cycle process that cause the most? And so along the x-axis here, we have the different steps: synthesis, separation, purification, functionalization. Here we have the embodied energy, and note these are in gigajoules per kilogram. Now, you'd never have a kilogram of a nanomaterial in a device, but it's scalable. And you can see these are the different materials. So this in blue is the carbon precursor, the carbon material that you use to make it. But here are some other steps, like the solvents, solvent regeneration. So it turns out that it's not just the material you used, it's all the processing along the way, here like the purification, that actually contribute to this. And then we can go back and use this for design. We actually analyzed a whole different array of methods of producing this, and we said, well, there's pyrolysis methods, there's plasma and things like that. The pyrolysis actually turns out the best, which you might not expect because you'd think it would be very carbon intense. But anyway, so this was actually a really interesting finding. So just because a material is used in a small amount doesn't mean it's no impact. You have to do the LCA to find out. And then when you look at some of these materials, so again, fullerenes, carbon nanotubes, really huge, 200 to 600 gigajoules. Okay, now let's put this in comparison. Aluminum is one of the high energy materials we often talk about. Aluminum, maybe close to 200 megajoules. So these are materials that have huge order of magnitude difference in terms of their embodied energy, which again is the total amount of energy that you pour into the system to get your material out. And then, of course, you have concerns about the toxicity or the environmental impact. So nanomaterials, because of their quantum confinement, because of the size, behave in some different exhibit different properties. Those are properties that are really great when we want to put them in a device. Those are also the properties that may make them more toxic when we put them out into the environment. And so you have a number of different transport routes. They do get absorbed in different ways. The materials change quite a bit once they're released. And there's a lot of public fear over this. We don't know how much of that is actual versus would be a concern. Many of them agglomerate quite a bit and deposit out, which might be an impact for like bottom feeding fish. There's been some early studies that say like inhalation of carbon nanotubes or exposure can cause some health adverse effects. But the point is that we're already making these. There's not like, let's wait and see what their impacts are before we decide whether or not to create these materials. Only last year did OSHA even come up with the very first standard for occupational exposure to nanomaterials, and it's just for one single type, carbon nanotubes. We're producing these in our factories, we're putting them in products, like Oreos. Did you know? Every time you eat an Oreo, you're eating nanoscale titanium dioxide. We're putting them in materials that we might not expect without any sort of oversight. And so this idea of being more proactive about understanding the risks of a technology is key. Now, the last kind of piece of this that I want to talk about is material criticality. Have you all heard the term critical materials, criticality? Okay, some folks have. When we think about materials, we often just think about scarcity. Like, is there enough of the material that we can use it for whatever we want? But there's a few other pieces to this puzzle. One of those is really just this supply risk. Is there a risk that we're going to run out? This might be a real physical limit, like there's only so much in the Earth's crust that we can mine. It might be an economic limit, like rare earth elements. They're actually not that rare, they're relatively abundant, but they're only there in really small concentrations. So it's not economically feasible to try to mine them unless you can get them in high concentrations. And then there's some social and geopolitical issues. Maybe all of the mines of a certain material are in one single country. And if that country enacts certain limits to exports or mining, then we're screwed. Okay, but then there's some other dimensions to this. There's also the vulnerability to supply risk. So say, let's see, maybe like tungsten or something like that. We run out of tungsten. Well, it's still used in a lot of materials, but not as much as it was maybe 20 or 50 years ago. So if we actually ran out of it, maybe there would be some alternate substitutes that could take place. But if we run out of indium, we're all in big trouble because there are no effective substitutes. And that would create huge impact because of all of our demand for it in electronics. So, and then we also have an environmental dimension. So by extracting and using this material, does it create these health impacts that we've been talking about? And one of the key leaders in this field is Tom Gradell. He's just retired. He is in the process of retiring from Yale and really has done a lot of really interesting work about the criticality of minerals. And a lot of the attention in this is on energy systems because that's where we're putting all of these interesting materials. So they've done a lot of work, and what they have is a dimensionless criticality score. So I know some people are like, oh, what are the units? this incorporates a whole lot of different factors, and there's a lot of uncertainty around some of the numbers. So they've chosen to put this on like a relative scale. But what you can see here is on the periodic table, elements where there is a great supply risk, like we legitimately might either run out of it or our access to it might be restricted, are in red. So some of these, arsenic, but some of these are very important. Titanium, indium, silver, and others. And some are much more available. There was a lot of concern about lithium a few years ago in batteries. We think we probably have enough. But you can see there's certain materials for which we do legitimately have some concerns about the supply. But are those materials actually that essential for our economic function? A lot of that depends on how we get them. So one of the reasons that some of the materials are so scarce or that there's some access is because they're not actually, we don't actually mine for them. Like nowhere in the world is there a mine for indium. It's obtained as a byproduct of, say, zinc mining. Tellurium, so cadmium telluride solar panels, anybody work on those? This is a really common type of photovoltaic systems. Tellurium only is extracted as a byproduct of one kind of copper mining. And that form of copper mining is actually going down. Other forms are becoming more prevalent. So if we cut off that source of copper, we cut off our source of tellurium, which has a huge impact on photovoltaics. And so these minerals, many of these that you see in green here, are only obtained as byproducts of other more common materials. And their extraction, because they're in very low quantities, it can be very energy intensive. Now this is really seen particularly for the platinum group metals. It takes a huge amount of energy to refine these and extract them, and they're only available in a certain limited availability and locations. And then the other piece is the vulnerability to the supply restriction. So if the material was cut off, or if we actually did run out, how much would that impact our economy? And so we see a different set of materials here that have more issues, like manganese, for example, is slightly higher. Okay, well, manganese is one of the key materials that is being used in newer forms of lithium-ion batteries. It's used in like the batteries that Leaf and the Volt, the Nissan Leaf and the GM Volt use. All right, so maybe it's not lithium we should be concerned about, maybe it's manganese. And then the final piece of this are materials with low substitution. So we often think, as engineers, that whatever technical challenge you throw at us, we'll come up with a substitute. And it turns out that some materials have such unique properties that we do not know yet what those substitutes will be. Now, sure, they might come about. And those of you all doing really fundamental material science work, if I had to pick a material to work on, I'd pick one of these in red. So things like dyspropium, right? It's a rare earth element. It's used in magnets. And also phosphors and LEDs and things like that. Manganese we talked about. Magnesium. So there are some elements that are used for such specific purposes in applications that it will be very difficult to find substitutes that perform equally or even close to, you can see extremely poor performance versus excellent performance. And what's interesting is on this one, there's no blue. In the other ones we saw some, they were like low risk, they're okay. There's no blue here. There's no material that is an excellent substitute for another material. When you design a product or process, it always works best in the way that it's first designed. And here are some of the applications where we see some of the concerns. So photovoltaic films, magnets are a big issue, both for wind turbines and for electric vehicle motors, batteries. There's a number of issues in lithium-ion batteries. One that's not up here is LEDs. The phosphors that are used in LEDs are very unique. Like this dyspropium is one of the only ones I think that's used for like the blue in LEDs, which is a key feature of light. Consumers wouldn't accept it if it doesn't have the right color blend. And then there's been some work to try to rank these where you actually see something like how important the material is to clean energy and its supply risk. And so the ones up in the red are the really concerning ones. There's actually many, many, many versions of this matrix, and depending on who's doing it and what values, the materials move a little bit. But there's some commonalities. You see some of the these in red are pretty common to all of them. And then the final piece of this I want to talk about are wastes. Now, one of the first areas that I worked in is, I mentioned electronics a lot. And one of the issues that we see a lot on TV, looks really horrifying, is this idea of electronic waste. So you see these, burning wires to get the copper out, kids playing and washing in rivers that are polluted by electronic waste. And one of the reasons this waste stream is such a problem is that as these products were being introduced, no one thought about, hey, what should we do when they're broken? Does the US have enough recycling infrastructure to actually recycle them? Turns out no, and it's actually cost a lot to recycle them. You don't get a huge amount of economic return. So they're sent to places where you have a lot of manual labor, even if you get a low recovery. All right, well, can we take the lessons we've learned from this system and apply it more proactively to other waste streams? Like, what the heck do you do with broken solar panels or broken wind turbines? Or in the area that I work in, lithium-ion batteries. Like, New York State, for example, has actually passed a disposal ban on lithium-ion batteries. So you can't put it in the landfill. Well, where do you put it? There's no recycling infrastructure in New York State. Most of them right now actually get exported to California and then to Canada, where they're submerged in a vat of liquid nitrogen to remove the charge. They're ground up into very fine pieces, and then they're leached in very, very strong aqua regia, so hydrochloric and nitric acids. Super environmentally friendly process, right? The other alternative is we can ship them to Belgium, which is where Umicore is located, one of the biggest smelters in the world, where they process a lot of electronic waste. They can also throw the batteries in there. They get a little of the cobalt out, and that's pretty much it. And so we're developing these high-tech products with no thought about their waste. And so that's why I spend a lot of time thinking about, can we actually forecast this? How many of these battery packs are going to come out in the waste stream? What's in them? Are they recyclable given our current technologies, or should we develop new systems? But any technology that you introduce will eventually become waste. And you have to think of what you're going to do with it. And it also has to fit into the system. So a lot of times with bio-based materials, people say, oh, it's compostable, it's not so bad. It's only compostable if it's handled in that way. Okay, you can't just throw something in a compostable in a landfill. It's still going to degrade. It's still going to cause impacts. I mean, it'll degrade, which is good, but it'll also produce methane and other materials as it degrades. Okay, so these are some of the issues that I hope that you will appreciate that life cycle assessment gives us an understanding of, that we might not normally think about as we're just sort of going about our normal sort of engineering, design, chemistry, synthesis work, is that there's these other facets that are attendant to all of the technologies we develop. And I want to work through one final example and have a little bit of discussion to kind of close out this session. This first part is, let's actually think of an example. So I've mentioned it several times, but let's actually think about this electric vehicle example. What are the potential sustainability trade-offs? And what can we learn from life cycle thinking? So let's actually discuss this. Why should we use life cycle thinking on electric vehicles? What might we learn from it? And why do we need to think about the trade-offs for this system? All right, so jump on in. What do you think? Electric vehicles, what are some of the life cycle issues?
The new forms of energy use on that Sankey diagram, the amount of energy, electricity that went into vehicles was like less than 1%, and now that will just skyrocket with increased use. So that's something that hasn't been studied.
Exactly. So the point was that the form of the energy used will change. Instead of from petroleum to gasoline, we're now burning fossil fuels and getting it off our grid. So we have a new form of energy, a new way of delivering the energy, and different environmental impacts from that energy production. All right, what else? In the back.
The batteries.
Okay, the batteries. Tell me more. What about the batteries?
They're usually made of things that are expensive and hard to recycle, and then when people are done with them, they're going to have to take them somewhere.
Okay, exactly. So in a traditional vehicle, you have your lead acid battery. doesn't have a super great efficiency or life cycle, but it's a pretty well-established system. And it turns out we recycle like 90% of all the lead in the United States because there's a law saying you will recycle all the lead from these batteries. Okay, that policy has been enacted, and now we have that system in place. There is no such comparable system for batteries for electric vehicles, right? We just sort of talked about some of the waste stream. So you have different manufacturing impacts of producing it, and then you have a different waste stream. Right? What else? What are some other life cycle issues?
Creating charging stations that didn't exist.
Okay, so infrastructure. So not only do we have to think about the grid infrastructure, we also have to think about if you deploy this technology, you have to have somewhere to charge it. Some of these you can just plug into your regular old outlet. If you have the change to, if you have 70K laying around to buy a Tesla, you have to have a special Tesla charger. And that's another expense and another bit of infrastructure that we have to put into place. What else?
So people, like, would it be better to like introduce the new cars? Because like you don't recycle the old cars. Like someone sells them at you give them to the manufacturer and then they sell them at a reduced price. So you're just giving another car like to someone else, and then you're using a new car. Right. And that's like 6 billion people, or maybe 3 billion people using that. That doesn't really make sense.
Sure. One of the things we never think about in vehicles is the manufacturing versus the use impact. So you now have a vehicle, and if you're going to replace it, you have the energy you've already sunk into making the first one, right? And so have you kind of paid that off over the course of the driving, or are you replacing it very soon? What is the trade-off there? And then a lot of my colleagues are actually looking into questions like, what sort of energy savings or efficiency savings of the electric vehicle how much of savings are possible, and how does that compare with the energy that it took to make the vehicle? And like, how long do you have to drive it, or how quickly do you replace it to actually pay off that sunk cost? Did you have a point from earlier?
No, I was
Same?
Yeah.
Okay. Let's talk about the use though a little bit more. One of the things that gets a lot of concern is the electricity. So how do you think that plays out in the electric vehicle life cycle?
Depends if you're Ohio or California.
Yeah. So it actually depends in a lot of ways that are somewhat surprising. So there's a couple factors here. So you have how you get the energy, and then you have the conversion efficiency. There's a couple issues. Okay, so first of all, where you get the energy. Well, if you live in New York, we actually have one of the greener electricity supplies in the country because we have Niagara Falls. So we have a lot of hydropower. At the same time, that's hydropower that's already been allocated to some extent to existing uses. So for a small amount of vehicle adoption, you kind of are already capitalizing on the electricity that's available. If everyone adopted, now you're going to have to build a new power plant. Maybe that power plant is coal. So do you really get to claim the credit for the regional average, or is this a marginal effect? You add this demand and you add this capacity. So there's a question there. But in general, one of the things that we're going to go through an example in the next session. In general, what you find is if you have a fuel mix that's mostly natural gas or cleaner, then electric vehicles, the life cycle carbon footprint comes out pretty comparably to gas powered. But if you have an electric grid that's dominated mostly by coal, it can be much worse. Now, the pollution is happening in a different place. So if you live in a really congested urban area, maybe that's actually not a bad thing because you're reducing some of those the smog forming, the particulate matter. I lived in both Atlanta and in Phoenix, and in both places they say they're in parts of the year when you run outside or you exercise outside, it's like the equivalent of smoking a pack of cigarettes or something like that, because I don't know if that's true or if that's just a colloquialism, but people say that because it's so smoggy and you're kind of inhaling all of this pollution. So in those cases, maybe it's a worthwhile trade-off. You have more CO2 being produced here if you can clean up the air here. There's no scientific way of actually determining which one is better. It's a value decision. The other part of this, the regional issue, is the battery performance. So batteries work pretty good within a relatively average temperature range, but if it's really cold or really hot, their efficiency goes down. So there's parts of the country where it's actually greener to use different technologies. And then you lose a lot of energy along the way. There's a conversion efficiency as the vehicle's running. The conversion efficiency is pretty low for lead acid batteries. So if you have a green supply chain of your electricity, you can do a lot better for the lithium-ion batteries because they're much more efficient in terms of the amount of energy they can deliver compared to what you put in. So there's a lot of regional differences. What else? Other thoughts? Yes.
Sort of a question.
Sure.
You've talked about the rare earths and uranium and stuff being very critical and stuff, and yet we're putting a lot of it in landfills and stuff. Has anybody done the study to see about recycling, whether it's more cost effective to start recycling this stuff? Is there economic reason to do such a thing?
That's a really great question. And a lot of it is really concentration dependent, and whether or not you can get a pretty pure stream of it. So one of the interesting ideas in the solar panel area is that you would actually have kind of a closed loop. So some of the companies like First Solar have said they make the CAD-TEL panels, the cadmium telluride panels. They actually have said, look, we don't want to our stuff to go into a landfill and then have to separate it out from all the rest of the waste. We want to just take back our own panels. And we're going to have this whole sort of closed loop supply chain. And in that case, it works pretty well because you know exactly what's in that waste stream, and it's pretty cost-effective, low contamination. Batteries are an interesting example because we're sort of changing what materials are used in them. We right now are recycling for the cobalt. The cobalt's scarce and expensive. So battery, and it's also, you hear about the fires, right? A lot of that cobalt, this is very high energy density, very reactive. It's one of the it's less safe than other chemistries that are out there that use manganese or iron. But the problem is we don't recycle manganese and we don't recycle iron in that form. It's not steel, it's like a iron powder. We don't recycle in those forms from batteries. So it's not yet cost effective to do that because there's not a market for it. So in that case, it would actually take some sort of policy saying, you're going to do this recycling, or it'll take developing a market. So there has to be a demand for the recycled material. For the rare earth, there's a lot of interest in that right now. A lot of people are trying to come up with rare earth recycling technologies. And even to your point about the landfill, there's a number of researchers who are actually looking at landfill mining. So at some point, these materials will become more concentrated in our landfills than they are in the ore because we're depleting the ores. And so there's a number of people looking at how do you actually go back in and mine old buildings. You think about, some people do that a lot, copper getting taken out of old buildings. That's a form of urban mining, but maybe that we could do it more intentionally, or we could look at certain landfills. I even have some colleagues that propose what they call a monofill. So this is the idea that, hey, look, here's this material. We don't really have a good recycling technology for it yet, but instead of throwing it with the rest of the waste, let's make its own designated landfill. So it's all electronics. And in the future, when it becomes more cost efficient or more priority, here we'll have the stockpile of the material. So there's, it sounds a little bit crazy, but there are some, it may be more effective over the long term to do that. And again, that gets back to the systems thinking idea. Yeah, so I think we touched on most of the ones that I was going to mention. Whoa. We have to produce the vehicle and the battery, right? You have to produce the electricity. You have to think about the fuel type, the source, the efficiency of the conversion, and the efficiencies in the charge and discharge. And then at the end of the day, you have to think about these waste streams. So this is just a common example, and we're actually going to go through in I sort of call this first lecture the why of LCA. In the next one, we're going to go through the how of LCA. What are the actual methods that are used, and how can you sort of understand if it's applicable to your research? And we'll keep coming back to this electric vehicle case study because I think it's an interesting case. And it's one where, like other things, there's a lot of misperception. How many of you all have heard the story like, it actually takes more energy to make a solar panel than it does to use it, or it takes more energy to make the battery than it does than you save. A lot of those are kind of public misperceptions. The technology is no longer that inefficient, but we're going to keep on using that as an example. Okay, so I'm done for now for this first, and I think we have a break.
Yeah, for 15 minutes.
15-minute break or so. But questions? Yes?
Sort of a big picture question. So there are a lot of issues, obviously, with various materials that are used in things that on the outside, at least, are
Right.
sustainable.
Right.
And then when you think about working at a university, you think about getting grants to fund your research. And a lot of the funding agencies have areas that are kind of hot that they want people to
Right.
submit grants on.
Okay.
Do you know, or can you comment on how some of this information gets into the sort of big picture of the policy of what should
Yeah.
be funded?
Yeah.
Does that?
That's a great question. And of course, I don't know that I can comment so much on the science policy side, so like how the funding allocations are actually influenced by this. But I think there's a few key areas where there is enough of an area of interest where that you're going to get a little bit of traction. So we talked about some of these critical materials. Well, there's actually a lot of funding interest in these, not from a sustainability perspective, but from a defense and security perspective. So the more reliant we are on politically unstable countries, and the lower the stockpile that we have in the United States of these materials, the more vulnerable we are. So there's actually, like, the Defense Logistics Agencies just put out an RFI for funding on critical materials. And so any sort of analysis that would go into that would certainly have a sustainability piece to it as well. The other area where I think there's a lot of traction is sort of when we think about infrastructure. So a lot of our infrastructure in the United States is aging, and the electricity grid is certainly an example of one where there are challenges. And so that has a lot of sort of human interest, health issues, reliability, economic linkages, but then there's also the sustainability side as well. So I think there's the places where you've got these crossovers between key economic issues in sustainability or in society, and then there's also sort of a parallel or even sort of tangential sustainability issue. Those seem to be where we see some of the funding happening. One, for example, NSF this year has said, look, we're really concerned about food, energy, water nexus. Okay, and they've said there are workshops and some supplements for now, but they anticipate a funding call for this in the future, where we're saying, you know, we have to think about food is such a key issue. It's a resilience issue, it's a health issue, but whatever food that we produce, there's also energy and water implications as well. And the energy-water nexus is one that's been around for a while. But it's definitely a challenge, and some of these, though, and this is what I would really encourage you all to be thinking about, what a lot of funding agencies do seem to like or be willing to accept is parallel investigations of the technology advancement and then some sort of coupled sustainability. So, you know, you're doing the fundamental research, but then you're also sort of thinking about these attendant environmental risks. State agencies are also really interested in this because you can usually translate a lot of these environmental things back into metrics that they're interested in, like jobs created, emissions reduced, landfill waste saved, because all of those are cost points for the state. I don't know if that's an exact answer, but I think there's certainly some key areas right now that are both hot from a sustainability side and hot from some other social or economic, and those seem to be where we can get traction. And that's kind of how I ended up in the areas that I work in, because we sort of just threw a bunch of stuff out there, and then what stuck was whatever those cross-cutting issues were. Great question. Other questions, comments? All right, we're going to take a break. We're going to come back in about 15 minutes, and then we're going to actually talk a little bit more about, I've talked a lot about energy. I'm going to switch gears and talk a lot about LCA, like a little bit more into the nitty-gritty of how we use it, how we do it, all of that. Okay?